convolution property. Convolution property of the Z transform. Okay, and I believe it is property number 9 in the table. Okay, so what we have is two sequences who have the following Z transforms, x1 of Z and ROC Rx1, x2 of N with the Z transform, x2 of Z with the region of convergence Rx2. Okay. And we are looking to find out what is the Z transform of x1 of N convolved with x2 of N. All right, let us take, and you know the expression for this, of course, we have already written this down many times. This will be k equal to minus infinity to infinity, x1 of k, x2 of N minus k. That is the expression that we have. Okay, now we want to know what is the Z transform of this particular sequence. So therefore, we say that this is N equal to minus infinity to infinity. We will copy this sequence because we are going to compute the Z transform of this particular sequence. So I will put brackets around that. This is the new this is the sequence, and Z power minus N. Okay, this is what we are trying to compute. Okay, so I am going to just do some simple manipulation of the sequences. So I am going to write this as interchanging the order of summation. This will be summation k equal to minus infinity to infinity. x1 of k comes out. The second term is summation N equal to minus infinity to infinity, x2 of N minus k Z power minus N. Okay, I am going to multiply by Z power k and Z power minus k. Combine these two together, what you get is Z power minus N minus k. So one more step of simplification. Summation k equal to minus infinity to infinity, x1 of k, the second term Z power minus k comes out, does not depend on N. The inner summation is summation N equal to minus infinity to infinity, x2 of N minus k Z power minus N minus k. Okay. By a simple change of variable, we can show that this term is nothing but x2 of Z, the Z transform of x2. This is nothing but the Z transform of x1 of Z. Okay, so the Z transform of this particular sequence, x1 of N conjugate x2 of N, is the product, just like we had a same relationship in the discrete time Fourier transform. What we get is the product of the Z transforms, x2 of Z. And remember, the right hand side must exist, both terms should exist. So therefore, the ROC will be Rx1 intersection Rx2. And also keeping in mind that when you have a product like this kind, there can be pole zero cancellations. So you must take into account, it is intersection, but take into account possible pole zero cancellations. Take into account pole zero cancellations, because if some poles are cancelled, then the region of convergence can change. Pole zero cancellation. So very, very important that we get this particular expression that we are able to work with. Okay. So what is the convolution property? It says if I convolve x1 of n with x2 of n, then what we will get is the product of the Z transforms. Okay. This leads us to another important application which is very useful for us in the context of the signal processing and communications, which is a function called the autocorrelation. Autocorrelation. Okay, now the autocorrelation of a sequence x of n is usually denoted as Rxx of n, because you're correlating x of n with itself, and it is defined as summation k equal to minus infinity to infinity x of k into x of k plus n. It looks very similar to convolution, but you have to be very careful because the second term in a convolution will be x of n minus k. Now what you have is x of k, x of n plus k. That means you are not time reversing one of the sequences. Both sequences are in the same orientation. If it's right sided, both, but you're going to shift them. And then you're going to correlate, which means you're going to multiply and then add them together. So the important difference with respect to convolution. Okay, in convolution, one of the sequences is time reversed. Here, no time reversal. Okay, basically you're doing the correlation with the sequences in the same sequence, but differences. So now I want you to let me compute what is the autocorrelation of this sequence, the Z transform of this sequence, of the autocorrelation sequence. So we'll call that as R subscript XX of Z. And we will do it in exactly the same manner. This will be summation n equal to minus infinity to infinity, and within bracket we will write down the expression, the time domain expression, which is k equal to minus infinity to infinity x of k x of n plus k. Okay, and this will be z raised to the power minus n. Okay. Do exactly the same steps, which is changing the order of integration, order of summation. So it becomes summation k equal to minus infinity to infinity x of k, and inner bracket will be summation n equal to minus infinity to infinity x of n plus k z power minus n. Okay, I am going to multiply by z power minus k and z power plus k. These two terms combined is going to give me z power minus n plus k. So one last step, this will be equal to summation k equal to minus infinity to infinity x of k z power plus k. Remember that whatever the term that is left over is plus k, and summation n equal to minus infinity to infinity x of n plus k z power minus n plus k, and we can show that this is nothing but x of z. And what is this? This is x of 1 by z. Remember, z has all instead of minus k, you got, so this you get this when you have when you replace z with minus z. So Rxx of z is given by x of 1 by z x of z. And I want to know the region of convergence. The region of convergence for this one, if it was mod z greater than RR less than RL, what will it be for x of 1 by z? It will be mod z greater than 1 over RL less than 1 over RR. Okay? So now what we need to do is look at the intersection of these two regions of convergence. Okay. Now I have two terms, mod z less than 1 by RR, mod z less than RL. Now remember, for left-sided sequences, what should you do? Take the innermost pole. So what is ultimately going to be the intersection point will be mod z less than, we should take the minimum of these two because you want to look at the left-sided sequences, right? So it is a minimum of RL comma 1 by RR. Similarly, look at the right-sided sequences, the other set of conditions, mod z greater than RR or mod z greater than 1 over RL. Combine these two right-sided sequences. One is a pole at RR, the other one is a pole at 1 over RL. But for right-sided sequences, you must take the largest of the values. So mod z will be greater than the max of RR 1 over RL. Okay. So the intersection point is given by mod z greater than the max of RR and 1 over RL. That's the left boundary. Okay, and why did it come out to be that? One case it is governed by RR, the other case is governed by 1 over RL. If you want the intersection of the two, you must take the maximum of that. Less than the minimum of RL comma 1 over RR. Now, if you are able to look at the expression for autocorrelation and derive the expression for the Z transform of the autocorrelation and recognize that what we are saying is that the Z transform is x of 1 by z and x of z multiplied. Now, this basically tells us what is the ROC of x of z, what is the ROC of x of 1 by z, how do I compute the intersection point. If I am able to get to this position, then what we have is a complete understanding of what the Z transform is, what the ROCs are, and how I should apply it in the context of convolution, in the context of correlation. Okay. And this will be a powerful tool for a number of applications which we will be studying. And one final concept for today, I would like to end with that. This is called the initial value theorem. Initial value theorem. It's actually a very simple result. So look at it in the following aspect. If x of n is causal, okay, what does this definition mean? X of n equal to 0 for n less than 0. And we also are going to make the assumption that x of 0 is not equal to 0. So basically it starts at the origin and then there are non-zero values that are present. Okay, then help me write down x of z. X of z will be summation, this will start at 0 and go all the way to infinity. X of n z power minus n. No negative powers because it's a strictly causal sequence and the sequence starts at n equal to 0 because x of 0 is not 0. So this can be written as x of 0 plus x of 1 z inverse, x of 2 z minus 2 and so on. That's the long version of it. Now, here is an interesting simple limit that I would like you to calculate. Limit z tending to infinity x of z. So, wherever there is z, you substitute z value which is very large going towards infinity. So, if z is tending to infinity, 1 over z is tending to 0. Okay, that is the condition. So, what you will get is x of 0 plus 0 plus 0 plus 0, all the positive powers of z will contribute 0 because 1 over z is going to 0. So, the initial value theorem states that limit z tending to infinity x of z for a causal sequence. What will this be equal to? It will be equal to the constant x of 0. Okay. Very useful property because sometimes we may not be interested in computing the entire sequence. We just want to know what x of z is. In that case, you take x, we want to know what x of 0 is. So, you take the expression for x of z and then substitute this limit. So, for example, this is a case where we know the answer, but just to apply it, a power n u of n. Okay, so this will give us a z transform x of z which is equal to 1 plus a z inverse plus a squared z minus 2 and so on. This will be 1 over 1 minus a z inverse. Okay. So, what is x of 0? Supposing I was interested in computing x of 0, I can either invert the entire sequence and then look at what x of 0 is, or I can say take limit z tending to infinity 1 over 1 minus a z inverse. In this case, we already know the answer, but we are still going to apply. So, z tending to infinity is 1 over z going to 0. So, therefore, what I will get is 1 over 1 minus 0 which is equal to 1. Which is what we get. So, you do not need to compute the inverse z transform, all you need to do is, as long as you know that it is a causal sequence, then you can write down the expression for x of z, apply the limit z tending to infinity, and then you will get the answer as x of 0. So, this is the initial value theorem. So, let us summarize what we have covered so far in today's discussion. Okay, we have been able to look at all of the remaining properties, the conjugation property, computing the real and imaginary parts, looking at the conjugated time reverse sequence, so therefore where you get the reciprocation of the ROC, and finally we have computed this sequence. We have also computed what is the z transform of Rxx of n, autocorrelation of x of n. We got it as x of 1 by z x of z. Okay, and this was one where we got the z transform relation, the ROC, as the min of RL comma 1 over RR greater than max of RR 1 over RL. Okay, so we computed that, and also we have looked at the initial value theorem. So, with this we have completed all of the parts of the Z transform. What is left is how can we compute the Z transform, and we will look at some very simple ways of computing the inverse Z transform using the property that we have here, the Z transform table, and also the Z transform pairs that we have. So again, we will look at this, and that will conclude our study of the Z transform, and then we will start a new section on the study of LTI systems, looking at it in the frequency domain. So we will stop here and then pick it up from here in the next session. Thank you.